Hi there, this is Heath. We're starting 14.7 today. We're going to spend 2 days on this section. I will have some notes today, and then I'm going to have some more notes, some more examples up on Wednesday. But we're going to spend 2 days on this section. It's a fairly long section, and I want to make sure that we go through this pretty carefully. I hope y'all had a good weekend. Let's go ahead and get started on this section here. So at this point, we're ready to start discussing critical points and extrema for multivariable functions. We're going to talk about local extrema today. You may have called these relative extrema in the past. Local or relative extrema. Absolute or global, you may have also called these global, depending on where you learn this. And we'll cover those kind next time. In the book, they're all combined into a single section, but I'm going to split this up over a couple of days. It's a lot of material for a single day. So that's our plan. So this is what we did back in single variable calculus when we wanted to find critical points. We would take the function, we would find the derivative, we would set the derivative equal to 0 and then solve for x. And then we also had to consider places where the domain, points in the domain where the derivative was undefined. That we could have a critical point, say, at a corner on a graph like on an absolute value function. The derivative was undefined there, so we also had to check for places where the derivative was undefined. Once we had the x coordinates where the critical points were, if we needed to know what the y coordinate was, we had to go back to the original function to solve for y. So this was a sort of a four-step process that we had to check for. Take the derivative, set the derivative equal to 0, check for any corners or sharp points on the graph, and then go back to the original function to find the y coordinate. We do not change this process. Here's the process in the multivariable case. The only difference here is that we're now finding both partial derivatives, and we're setting both partial derivatives equal to 0. Another way that we can say this, setting the partial derivatives equal to 0, is that we're setting the gradient of the function equal to the vector 0, 0. The gradient is the vector that contains the partial derivatives. We saw that on Friday. And so you'll sometimes see this idea here, but it's the same thing. We have two partial derivatives. We want to set them both equal to 0, and that means solving for x and y. And then, just like before, we have to include any points in the domain where the partial derivatives are undefined. And then if we need to find a z-coordinate, we have to go back to the original function to find a z-coordinate. Okay? So this takes a little bit longer because we have two equations we're having to work with. And when we have two equations, we also have two unknowns. And so this is solving a system. And that's a little bit more algebraically demanding, but the concept is the same. So I'm going to go through a couple of examples of finding critical points of a multivariable function here. And you'll see that the algebra is a little bit messier, but conceptually, this is what we were doing in single variable calculus. So here's the first example. We want to find the critical points for this function right here. And so what we need to know first is what the partial derivatives are. So the partial derivative in the x direction is y minus 2x minus 2. And the partial derivative in the y direction is x minus 2y minus 2. Okay? The second step is we're going to set these equal to 0. We can say that in terms of the gradient vector, or we can just say set f of x equal to 0, or the partial derivative with respect to x equal to 0, and f sub y equal to 0. So this is y minus 2x minus 2 equals 0. If I rearrange some terms here, this is negative 2x plus y equals to 2. And then the other equation is x minus 2y minus 2 is equal to 0. Well, that's just x minus 2y equals to 2, bringing the 2 over to the other side. All right, how might we solve this? There are a couple of ways we can solve this. But one way we could do it is to notice that x is equal to 2 plus 2y, and then we could substitute that in up here. And then try to find out what y is, and then find out what x is, for example. So there are other ways we can do this, but if we say that x is 2 plus 2y, then negative 2 times 2 plus 2y plus y is equal to 2. This is equation 1. This is equation 1 again, just with a substitution for x. So negative 4 minus 4y plus y is equal to 2. Add 4 to both sides, and we get 6 on this side. And we get negative 3y is equal to 6, and so y is equal to negative 2. And since y is equal to negative 2, x is equal to 2 plus 2y, which is 2 plus negative 4, and x also is equal to negative 2. And so we now know that x is equal to negative 2 and y is equal to negative 2. Are there any places in which these partial derivatives are undefined? No, we're not dividing by anything or taking the square root or doing anything weird with trig functions. There are no places where fx or fy is undefined. So we don't have to worry about those kinds of critical points. So then the last thing we have to do is figure out what z is. Z, we go back to the original function now, and we get z is equal to negative 2 times negative 2 is positive 4, minus negative 2 squared, minus negative 2 squared again, minus 2 times negative 2, that's plus 4, plus 4, plus 4. This is confusing because all of these terms turn out to be 4s, but they cancel out nicely. This term is positive, this term is positive, this term is positive, and this term is positive. I have 4 positive 4s and 2 negative 4s. So this one cancels with this one, and this one cancels with this one, and I'm left with 8. So the critical point is negative 2, negative 2, 8. All right. Again, this wasn't hard, but it takes a lot longer than it does in a single variable case because we're having to solve a system here. This step 2 is the long step. Okay? Let's try another example. Let's find the critical points for this function. The first thing we want to do is take the partial derivatives. So the partial derivative in the x direction is 6xy minus 6x, and everything else goes away. And the partial derivative in the y direction is 3x squared plus 3y squared minus 6y. Is that right? 3x squared plus 3y squared. This term goes away, minus 6y plus 2. That's it. Okay? We're going to set these equal to 0 and solve. So we get 6xy minus 6x equals 0. And we get 3x squared plus 3y squared minus 6y equal to 0. I want to focus on this equation first, because this one factors nicely. We can factor this into 6x times y minus 1 is equal to 0. And so we get 6x equal to 0, and we get y minus 1 equals 0, which is y equals to 1. And so we have two possibilities from this equation. This does not mean that x equals 0, y equals 1 is a critical point, because we haven't checked in this equation yet. So we do not know if 0, 1 is a critical point. Because we only are getting these possibilities out of one of these two equations. But one possibility is that x equals 0, one possibility is that y is equal to 1. And so let's check those two possibilities. I'm going to use color for this step to separate them out. So in the possibility that x is equal to 0, we have 0 plus 3y squared minus 6y is equal to 0. I can take out a 3y, so that leaves me with 3y times y minus 2 is equal to 0. And I get two possibilities. Y is equal to 0 and y is equal to 2. And so when x is 0, y can be 0 or 2, but not 1. In other words, I get 0, 0 something and 0, 2 something, but I don't get 0, 1. And so this turned out not to be a critical point. But let's keep going. We also have the possibility when y is equal to 1. When y is equal to 1, this becomes 3x squared plus 3 minus 6 is minus 3 is equal to 0. That factors into, take out the 3, I get x squared minus 1 is equal to 0, and so x is equal to plus or minus 1. And so we get positive 1, 1 and something, and negative 1, 1 and something. When y is 1, x can be positive or negative 1, but not 0. So once again, this is not a critical point. And so that's what we got at the end of step 2. Step 3, we have to check for any places where these are undefined, but there aren't any. So step 3, there are no places where fx or fy is undefined. But step 4, we have to fill this out and get the z-coordinates. Use the original function to find z. Well, that's just a matter of doing some calculations. When I plug in z into the original, when I plug in 0, 0 into the original function, everything turns out to be 0 except for the last term. I get a 2. When I plug in 0, 2 into the original function, this is 0 plus 8 minus 0 is still 8, minus 12 is negative 4, plus 2 is negative 2. When I plug in 1, I get 1 plus 3 plus 1 is 4, 4 minus 3 is 1. 1 minus 3 is negative 2. Negative 2 plus 2 is 0. And then finally, when I plug in negative 1 and 1, this is going to be 3 plus 1 is 4. 4 minus 3 is 1. 1 minus 3 is negative 2. And plus 2 is also 0. And these are our 4 critical points. So this function has a lot of critical points. The last function only had 1. Okay? So I'm hoping this makes sense, that we're not doing anything conceptually new. In single variable calculus, we found the derivative and set it equal to 0. In multivariable calculus, we just happen to have 2 partial derivatives, and we have to set them both equal to 0. And that gets us something a little more complicated to have to work with. Okay? So again, this is the hard step, is actually working out the algebra here. All right, so now we have these critical points. How do we tell if they're maximums or minimums? Let's move on to this next section. So testing critical points in 3 dimensions to see if they're maximums or minimums is complicated by the fact that there are places where the concavity is not the same in all directions. At this marked point on this graph here, and I'll do this in red so this shows up nicely, the concavity depends on whether we're going in this direction. Since the graph is concave down, this is a minimum going left to right, but going from back to front, this is concave up, and this is a maximum going front to back. We call this point a saddle point. Because it has 2 different concavities at the same point. It's concave up in one direction, it's concave down in the other direction. And that can't happen in a single variable case. And one way we would use to test critical points was to use the second derivative test to see if the graph was concave up or concave down. The second derivative test is going to give us conflicting results here. And so we have to do an additional test to see if we have a saddle point. We have to add an additional step. Okay? So here's how we're going to test critical points in 3 dimensions. First of all, we need the second derivatives, and there are 4 of them. The partial derivative of xy, the partial derivative, this should be xx. Sorry about that. Partial derivative of xy, the partial derivative of yx, and the partial derivative of yy. But this one and this one should be the same. By Clairaut's theorem. Unless the function has an infinite number of discontinuities that we can't isolate, these 2 are going to be the same. So we really only have to find 3 partial derivatives. We just have one of them show up twice. This is the new step. We're going to use what's called the saddle point test, and I'll show you the saddle point test in a moment, to test to see if the critical point is a saddle point. If it is a saddle point, we're going to just stop right here. Because if it's a saddle point, it's not a maximum, it's not a minimum, it is it's a saddle point. It's a maximum only in one direction, and it's a minimum but only in one direction. But it's not a maximum in all directions, and it's not a minimum in all directions. If the critical point is not a saddle point, then we're going to test AB in the second derivative, fxx. That's this first one that we found here, the one that I typoed. And we'll test the concavity. If the graph is concave up, the critical point is a minimum. If the graph is concave down, the critical point is a maximum. And if the concavity is 0, well, that's that inconclusive case for the second partial derivatives test, where we don't have the computational tools to test this critical point. We'd have to graph the function instead to see what is going on. Okay? So, this is so much simpler in single variable calculus. We just found a partial derivative and then tested to see if it was positive or negative or 0. But we have this new test that's called the saddle point test. Okay, so let's talk about how the saddle point test works. I'm going to get to this business about the matrix first in a moment, but let me talk about the idea. We have 4 partial derivatives. The 2 that use the same variable both times, fxx and fyy, these measure concavity. If fxx is positive, the graph is concave up in the x direction. And if fyy is positive, the graph is concave up in the y direction. But the mixed partial derivative, this one here, fxy and fyx, and again, these should be equal, this measures what's called torsion. And torsion has to do with how twisty the shape is. And I mean, I'm not describing that very well. But if the torsion outweighs the concavity, then the shape twists so much that it can be concave up and flip around to be concave down at the same point, the way that a saddle point does. In a saddle point, there is so much torsion that the curving upwards of the concave up part flipped around, being twisted to being concave down, as if you rotate the shape 90 degrees. And so the question we want to know is, does the concavity outweigh the torsion, or does the torsion outweigh the concavity? So does the torsion outweigh the concavity? If so, we have a saddle point. If the torsion outweighs the concavity, we have a saddle point. That the torsion is strong enough to defeat the concavity so that the concavity flips to the opposite concavity just by rotating the shape. That's the idea. If the concavity is strong enough to withstand the torsion, then we have the same concavity all the way around, in which case we don't have a saddle point. It's the same concavity as we rotate the shape. Okay? And the way we're going to do this is we're going to take the 2 concavity values and multiply them together. So we're going to multiply fxx times fyy. And we're going to take the 2 torsion coefficients and multiply them together. Again, these should be the same. And we want to know which one's bigger, if this one's bigger or if this one's bigger. And the way we can do that is to take their difference and see if the difference is positive or negative. And when we subtract these 2 values, the value we get from taking this diagonal and the value we get from this diagonal, we call that the determinant of the matrix. If you've already taken linear algebra, you're familiar with determinants. If you remember cross products from chapter 12, we talked about determinants then also. And so this is actually a determinant operation. We're using the concavity coefficients versus the torsion coefficients here. That's what's going on here. If the determinant is negative, the torsion coefficients win out. There's enough torsion to defeat the concavity in one direction and flip it around to a different concavity in a different direction. And that means we have a saddle point. If the determinant is positive, then the concavity coefficients win out. They're stronger than the torsion, which means whatever concavity we have, if it's concave down in one direction, it is concave down all the way around. And so we get, we don't have a saddle point. So if the concavity beats the torsion, in other words, the determinant is positive, then we have a shape where it's concave up all the way around, or concave down, but it's concave down all the way around. If the torsion beats the concavity, which means the determinant is negative, that's the saddle point shape where we have a point where the concavity is being twisted from concave down to concave up by the torsion that's present. Rotating the shape causes the concavity to invert. Okay? So that's the idea. We're testing concavity versus torsion when we calculate this determinant. And that tells us whether we have a saddle point or not. Little bit of trivia here. The determinant is called the Hessian of the function. You don't need to know that term, but if you look this up in some books, they will use this notation for the term. Capital H comes from this name Hessian. It's named after a German mathematician that did some research. Oh gosh, back in the very late 1800s on how to calculate saddle points. All right. There are some special cases where the determinant turns out to be 0, and again, when you get a 0 result, you just have to use a graphing tool to see what happens. The computational tools we have don't work in that case. All right. So let's try an example. We already did this example before. We found that the critical point for this function was -2, -2, 8. What we want to do now is test this critical point to see if it's a saddle point. So we need some partial derivatives. The partial derivative in the x direction, we did this before, was y minus 2x minus 2. The partial derivative in the y direction was x minus 2y minus 2. If we do the partial derivatives again, the partial derivative of x with respect to x is -2. The partial derivative of x with respect to y is 1. The partial derivative of y with respect to x, well, that comes from this. That's also 1. Partial derivative of y with respect to y is -2. These two are the same. which is how it should be. It's also true in this example that these two are the same, but that's not true in general. This is just a coincidence in this case. And so our determinant is, let me make this up, the Hessian, which we abbreviate H of xy, is the determinant of this matrix, -2, 1, 1, -2. The concavity coefficients, -2 and -2, are on the main diagonal, and the torsion coefficients, which are 1 and 1, are on the other diagonal. And that determinant is, we combine the concavities and we combine the torsions. And so we get 4 minus 1, which is 3. This is positive because the concavity wins out over the torsion. And since the concavity wins out over the torsion, this is not a saddle point. That's the important thing. Not a saddle point, because the Hessian is positive. Okay? So we have tested this critical point. We now know that it is not a saddle point. Okay? I'm going to come back to this slide in a moment, but I want to do some exposition for a moment. If the critical point is not a saddle point, then the concavity in any direction tells us the concavity in all the directions. When the concavity is strong enough to withstand the torsion, it doesn't flip by rotating it. It stays the same all the way around. And so once we know that a critical point is not a saddle point, either of the concavity coefficients tells me the correct concavity for the shape. And if the graph is concave up, the critical point is a local minimum. And if the graph function is concave down, the critical point is a local maximum. And so example 4 says to go back to example 3 and test this critical point to see if it's a local maximum or a local minimum or a saddle point. Well, we can do that now. I'm going to go back to example 3 now. We have already tested and showed that it was not a saddle point. And so the concavity coefficients tell me what the result is. Both of them agree. Both of them say the graph is concave down, because the concavity coefficient is negative. And since the graph is concave down, then the critical point has to be a maximum. We say it's a local maximum. And so that's what we have here. -2, -2, +8 is a local maximum. Okay? So that finishes off example 4. We did this, -2, -8 is a local maximum. Okay? Let me sum up all the steps that we did to get to this point. We've done a lot of work with this function. So the big picture here is that we found the partial derivative, found the critical points. And that involves setting the gradient vector equal to the 0 vector. And that involved solving a system. And in some cases, it might involve also checking for places where the derivative's undefined. Then we had to test for saddle points. Fxx and Fyy, measure concavity. Fxy and Fyx measure torsion. Which one is stronger? And then we had to, if not a saddle point, if it's not a saddle point, then we just had to test a concavity to see if it was a maximum or minimum. Concave up meant that our critical point was a local minimum, and concave down meant that we had a local maximum. Okay. All right. Let's try another example. We're going to find the local extrema for this function here, 4xy minus x to the fourth minus y to the fourth. Okay? So let's go through all these steps. So the partial derivatives, fx is equal to 4y minus 4x cubed, and fy is equal to 4x minus 4y cubed. We're going to set these equal to 0. I can cancel out the 4's in these equations, and this turns out to say that x is equal to y cubed and y is equal to x cubed. Well, there are 3 numbers that are cubes of each other. That is, x equals y cubed and y equals x cubed. The 3 possibilities are that x and y are both 0, x and y are both 1, and x and y are both negative 1. So we have 3 cases here. When x is 0 and y is 0, z is 0. When x and y are both 1, we have 4 minus 1 minus 1, which is 2. And when at negative 1, we also have 2. So these are my critical points. Okay. So now let's look at the Hessian. It's the determinant of this matrix here. We have to take the second partial derivatives. So fxx, we start with this function, we take the derivative again with respect to x, and we get negative 12x. Fxy, we start with fx, and we take the derivative with respect to y, and we just get 4. And then fyx, we start with fy when we take the derivative with respect to x, and we get 4. And fyy is we start with fy and we take the derivative with respect to y, and we get negative 12y. Okay? And we combine the concavity coefficients together, and we combine the torsion coefficients together, and we subtract 12 times 12. Negative 12 times negative 12 is 144xy minus 16. That's the Hessian that we have. Okay. So now let's evaluate each of the critical points. At the point 0, 0, 0, h of 0, 0 is 144 times 0 times 0 minus 16. That's negative 16. And since we have a negative Hessian, so 0, 0, 0 is a saddle point. Okay. Flat out, it's a saddle point. It's not a maximum, it's not a minimum. We have a negative Hessian. That's because at the origin, this is 0, this is 0, but 4s are stronger than 0s, and therefore the torsion wins out over the concavity. At the point 1, 1, 2, the Hessian is 144 times 1 times 1 minus 16. That's 128. That's not a saddle point. And in fact, at 1, 1, 2, negative 12 times 1, or negative 12 times 1, is negative. And so the graph is concave down. I just realized this should be negative 12x squared, and this should be negative 12y squared. Sorry about that. Doesn't change any of the calculations we've done so far. Sorry about that. If you were screaming at the video, you had every right to. Sorry about that. All right. Negative 12 times 1 is negative, and so the graph is concave down. And so 1, 1, 2 is a local maximum. So let's look at the last point. At the point negative 1, negative 1, positive 2. Here's where the square makes a difference. The Hessian is still positive 128. And this second derivative, negative 12x squared, is negative 12 times positive 1. And that's still negative. And so negative 1, negative 1, 2 is also a local max. And so we have identified all of the local extrema. The final answer is that there are 3 points that we have to identify. The origin is a saddle point. And 1, 1, 2 and -1, -1, 2 are both local maxima. Okay? All right. If you're wondering what that graph looks like with a saddle point and 2 local maxima, let me just sort of sketch out what's happening here. At 1, 1, +2, so we have a local maximum up here, and we have a local maximum back here at -1, -1, +2. But the graph between these 2 points dips down to the origin. So it goes through the origin. So this is 1, 1, 2. This is -1, -1, 2. This is the origin, 0, 0, 0. But because this is a saddle point in the opposite direction from this diagonal, the graph is heading down. And so what we have is this shape, and I'm terrible at being able to draw this, where this shape comes down from this point and then curves back up around, but then it's coming down from this point also. That's sort of the idea. And that this saddle point right here at the origin, it's concave up between the 2 local maximums, but then it's concave down in the opposite direction. Okay? You don't need to be able to visualize that to answer the question, but I thought maybe it would help to see that. All right, example 6. We have a delivery company that accepts only rectangular boxes, the sum of whose length and width. So let's sketch out this rectangular box here. And this rectangular box has an x-coordinate and a y-coordinate and a z-coordinate. And when we talk about the girth of the box, we're talking about the distance all the way around, which is 2x plus 2z. And the requirement here is that the sum of the length and the girth, so 2x plus 2z plus y, has to be less than or equal to 108. That's the restriction that they have. So what are the dimensions of an acceptable box of largest volume? Well, the volume is xyz, which is the same thing as x times, I'm going to substitute for y here, 108 minus 2x minus 2z times z, which is the same thing as 108x minus 2x squared minus 2x squared minus 2xz times z, which is the same thing as 108xz minus 2x squared z minus 2xz squared. All right, so that's our function. We want to find the dimensions of an acceptable box of largest volume. So let's look at the partial derivatives. In the x direction, the partial derivative is 108z minus 4xz minus 2z squared. In the y direction, the derivative is 108x minus 2x squared minus 4xz. And we would like to set these equal to 0 now to find the critical points. So we get 108z minus 4xz minus 2z squared equal to 0. I could pull out a z. In fact, I could go ahead and pull out a 2z. And I'm left with 54z minus 2x. I'm left with 54, not 54. 54 minus 2x minus z equals 0. And the other equation, 108x minus 2x squared minus 4xz equals 0. I can take out a 2x, and I'm left with 54 minus x minus 2z equals to 0. Well, this gives me two possibilities. 2z equals 0, or 54 minus 2x minus z equals 0. This gives me two possibilities. 2x equals 0, or 54 minus x minus 2z equals 0. But if 2z equals 0, then z equals 0 and there is no volume. And if 2x is equal to 0, the volume will be 0. And since our goal is to find the largest volume, these cannot lead me to a maximum. They might lead me to a minimum, they might lead me to a critical point, but they do not lead me to a maximum. And so let's go ahead and eliminate those. And let's just work with these two equations. I'm going to move the 2x into z to the other side, and I get 2x plus z equals to 54. And x plus 2z is equal to 54. All right. If I call this equation 1 and equation 2, one way we can solve this is to double the second equation. So we have 2x plus z equals to 54, and 2x plus 4z equals to 108. And then we're going to subtract. 2x minus 2x is 0. 4z minus z is 3z. And 108 minus 54 is 54. 3z is equal to 54, and so z is equal to 18. And then we solve and we find that x is also equal to 18. And then by going back and checking here, 108 minus 2x minus 2z, y turns out to be 36, is that right? 2 times 18 plus 2 times 18 is 72. 108 minus 72 is 36. So this is our dimensions, 18 by 18 by 36. But let's double check to see if it's a maximum. So the box is 18 by 18 by 36 inches. Is it a maximum? Well, let's look at the second derivatives. So the Hessian in this case. The second derivative, vxx, is going to be This is going to go away because there's no x in it. This will be negative 4z. And this doesn't have an x in it, so it goes away. The partial derivative of x with respect to z is 108 minus 4x minus 4z. And then this one, this should have been a z, not a y. Should have been, let's see, 108 minus 4x minus 4z. These should be the same. And with respect to z, this term goes away, and we get negative 4x. But we know that z is equal to 18, so this is negative 4 times 18 is negative 72. 108 minus 4 times 18 minus 4 times 18 again is 8 times 18 is 144. 108 minus 144 is negative 36. Negative 36 and negative 72. I can tell just by looking that 72s are more powerful than 36s, but 72 times 72 minus 36 minus 36 is positive. And so this determinant is positive. I don't want to calculate that out, but it's 72 squared minus 36 squared. And it's definitely a positive number. And so this top number here, fxx, actually vxx, because we're looking at volume, is our function, is negative 72, which is concave down. And so this point is definitely the local maximum. So did we need to do all of that extra checking? We probably didn't, but because we had sort of by reasoning eliminated the minimums here where the volume was 0. But it's a nice thing to be able to check that. All right? Y'all take care.